Computational scientist here at UT Austin. He is a lover of food, a father, an HPC expert, which is probably very highly related, a Pythonista, the co-organizer of this conference, a NUM-focused board member, and most importantly, a home brewer. So welcome, Andy.
So thank you for coming out for the second day. We have almost 900 tweets already, so I expect at least 900 more. It's my distinct pleasure to introduce our keynote speaker today. And so when we decided to do reproducibility, one name kind of popped in my head as someone who is in industry and actually leading the way, and has been leading the way for probably 20 years now, at least. In the movement of doing reproducible research and open source code. And so our speaker today is Dr. Will Schroeder, who got his math PhD at RPI, and at the same time he was working a job at GE developing VTK, and eventually turned that into Kitware with a number of folks, the VTK folks, to promote a open source environment for sharing the data. And VTK has kind of been one of those cornerstones of my career as far as, like, if every time I want to share my results, it's definitely the first thing I went to that most computationalists know. The Python bindings need some help with the documentation, so he's here, and we've got plenty of people who can help with that, and I expect pull requests. Matt has decided to chair those. Now, voluntold. But I want to bring up Dr. Schroeder, if you're ready.
Yep, ready.
And so the CEO of Kitware and lead developer of VTK. Thank you very much.
You can need it,
Huh? Oh, you need this thing.
I need it.
Okay.
It was funny yesterday coming in from, I've been in Europe for a couple weeks, and it's been a little bit cooler there. And so I flew in Monday, got in Monday night, lost my luggage, of course, took a day to debrief, and flew out yesterday. Of course, arrived in 103-degree temperatures. Took the bus from the airport, which was quite an experience because it was so hot in there, people were so tired that actually one of the guys in the bus, he actually fell over. I mean, he was just standing there 1 second, the next second he was fell over on some luggage. And of course the whole bus went silent. But then the guy got up a few seconds later and said he'd fallen asleep standing on his feet. So I sort of feel like that right now, and if I fall over, just prop me back up and I'll keep going. All right. So, good. All right, so I want to thank everybody here, SciPy, Matt, Andy, Leah, for setting up my accommodations and everything. It's been great. This center is fantastic. Really wonderful. It's sort of classy but low-key at the same time. So thank you very much for that. But anyway, the person I really want to blame is Matt, because he told me this would be an easy thing to do, no big deal. He didn't tell me about the heat. He didn't tell me about all this other stuff. And I thought I would just throw something together. I passed it by Matt initially, what I was thinking about doing, and he told me this was a classy audience and I needed to be a little bit more well-behaved. So that took care of 90% of my content, which I had to throw out. So hopefully I've come up with something that's reasonable, does you guys justice. And so the way I want to start is basically give you the punchline to the whole talk. My talk is called The New Scientific Publishers, and the punchline is we are the new scientific publishers. I think this is obvious to most of us that are following publication and scientific processes. The publishing model is really broken, and anyone that sort of looks into it knows this. So I think we all know it, but what I want to do is sort of tease out some of the ideas and some of the where we're coming from, where we're going to, and just sort of see where we might end up. So what I want to start with is giving you perspective from where I'm coming from so you understand what my motivations may be. First of all, I don't know very much about Python. I've been around a long time. I remember in the early 90s, people in our lab at GE Research started using Python and raving about how great it was. And I'm more of an algorithms guy, so I spend most of my time in C++ and such. But VTK, the system that I work on, has always had Python as part of it. And it's a great language, and actually it's probably the most widely used language for VTK right now in terms of putting together applications. All our tools use Python. Now, I do have a Python story that I'm going to share with you at the end, but you'll have to wait for that. So the other part of the perspective I'm coming from is I work at a company which is an open source company, and we have a portfolio that looks like this. It's not complete, but it sort of shows 5 key areas that we focus on. High performance computing, visualization, medical imaging, medical computing, data and analytics, and computer vision. And on top of all that is software process. We pride ourselves on being really good in the scientific computing world, but that also includes knowledge of software processes and writing good code and all that sort of thing. We have people on our team that have memorized the C++ manual and are really good at that sort of thing. The other part of the perspective is that we have an awful lot of open source tools that we create and co-develop with our communities. So many people know Kitware from CMake. Actually, a lot of people use CMake and don't even know about Kitware. That shows you how good our marketing efforts are. We're really bad at it. But CMake and C-, a lot of people use that. VTK, Andy referred to. ParaView is an application built on VTK, which is for scalable large data visualization. The Insight Toolkit, Matt knows all about that. He's one of the masters there. Our Kiwi VES mobile rendering platform. We're doing new stuff with large data, data analytics. We have a system called Tangelo, which is a web-based client-server application. We've got tools in open chemistry. We work with a medical imaging community doing 3D slicer. We have a data integration platform we call Midas. We have an image-guided surgery toolkit. And by the way, that was voted worst logo by some website somewhere. We take great pride in that. If you look at it closely, you can see a spine and a C scanner and some other weird stuff in there. And the last thing is the Common Toolkit, CTK, which is a biomedical framework for developing applications in that application area. And of course, I don't think this is a mystery to most of you, but our business model, being an open source company, is really very simple. It's services. We do technology integration, so we take our really cool open source stuff and we put it into people's workflow. And we do a lot of collaborative R&D. So there's probably people in this room that Kitware may have collaborated with, academics or other. And that's the bulk of where we make our living. And like I tell people in the family that aren't technically savvy, my cousins and such, really what we do is we take something like a tax code or a legal code, which is a free thing, anybody can get their hands on it, and we service it. So we're a lot like lawyers and accountants. I don't know if that's a good thing or a bad thing. But we focus on technology, obviously. All right, so that's where I'm coming from. I'd like to talk now about sort of the status quo of publication and just give you a sense of where we're going, or rather where we are. And the focus is on scientific publication. Obviously, the publishing field as a whole is struggling right now. But after all, this is a SciPy conference. Scientific is an important word here. So I want to focus on the scientific aspects, and that ties into the reproducibility issue that was mentioned earlier. So to begin, there's some really important words here. First of all, publish. It's important to remind ourselves what that means. It's to make publicly or generally known. We forget that sometimes. Sometimes scientists act like they're hiding things or hoarding things or preventing their competitors from knowing stuff. That's not what it's about. And, science has done great things for us. It's a systematic process of understanding physical material world. And it's important to remember that the roots of science are about understanding reality, understanding where we came from. It's about seeking knowledge, and it's about benefiting humankind. I think all of us agree that science has done wonders for the human race. And I want to keep that going. I think all of us do. And that's why reproducibility and the way we publish our results is so important, because science has had profound effect on us as a society, as a world, and we got to keep that going. All right, so, and finally, this is the way science is typically broken out by many folks, three legs of a stool, if you will, based on theory, methods and experiment, and data. Some people break out a fourth part, which is sort of a computational aspect, data-driven science, but I sort of lump that in with data. So these are the areas that we need to address if we're worried about reproducibility and we're worried about moving science forward. And because we're dealing with this publishing issue, it's really important to understand where we came from so that we can understand where we're going to. It's hard to say exactly when sort of the scientific method, science started. A lot of people point to the 1600s. René Descartes published this document, Discourse on the Method, which is really an articulation of scientific method. And he does a very good job of sort of arguing why reproducibility is so important, why experiments are so important, why you have to do things again and again and again until you can prove that they can be reproduced. But before this time, of course, the Chinese, Indians, Islamic empires, Persians even, all were doing various aspects of science. But the emphasis wasn't so much on the method and experiment as more of a way of collecting knowledge. So, science wasn't invented in the 1600s. It's been an ongoing thing. But I think the key principle of reproducibility and experiment sort of really came to the forefront in the 1600 time frame. And as a matter of fact, if you look back to around the 1660s, the Royal Society was formed. And they have a really interesting motto written there in Latin, which translates to take nobody's word for it. So these guys were really militant. I mean, think about it. You're a philosopher, a natural philosopher, and you're trying to make sense of the world. And there's all these competing theories about how the world works. And these guys say, look, the only thing that makes sense is if you can reproduce something over and over again, we know it's real. So that was sort of a cornerstone of their approach. And they were very, very militant about it because they were trying to cut through a lot of superstition and a lot of different ways of looking at the world. And that's important to keep in mind. Science is fundamentally a dangerous and very militant activity. It's about puncturing what we think should be true and trying to present what's really true. So very rapidly after the formation of some of these societies and approaches and methods, people started organizing into sort of a publishing model, which looked like this, where scientists would basically write letters to one another. They did crazy stuff sometimes, like write stuff in anagrams so that they sort of documented stuff without fully disclosing it. So that sort of secrecy aspect was even present back in the 1600s. Anyway, scientists would write letters to Royal Society. The Royal Society actually met in a place, probably in London, and they basically got together and tried to replicate experiments. So they sat down from the letter, tried to reproduce things, and really made sure that these things were reproducible. And eventually the society published these letters once they were validated in terms of replication, experimental replication, in Transactions. And this has been ongoing for many, many hundreds of years now. And it's evolved. And the publishing companies have done marvelous things for us. I don't want to come across as a basher of the publishing folks because I think they've done a huge service for us. But what's happened along the way, of course, is that it's evolved into something where scientists typically write papers, submit it to some sort of publisher, there's some sort of quote-unquote peer review, and of course these things are bundled into journals. Now the problem is that as science has become more complex, and computational methods have been emerging, this is starting to break down. And I think we all know this. For example, in the old days, it was sufficient to write a relatively short paper describing an idea, describing methods, describing data, because the methods and the data were fairly compact. They weren't large size, and they could be included into a paper volume or a paper document. But as we all know, since the advent of modern computing, of course the internet and so on, data and software, which are methods, are just exploding in size and complexity. So this whole notion that you can write an 8-page or a 20-page paper and capture what's going on in a scientific breakthrough or a scientific hypothesis is ludicrous, because you don't have the methods, you don't have the data. So we get papers now and we look at them and we say, well, yeah, that sort of makes sense, but we're not really reproducing the results. We're sort of validating based on our knowledge that, yeah, it sort of makes sense. I've done this, I think most of us have. But in the end, we're not really reproducing results. And the unfortunate part of this, from my perspective, being a computational scientist, is that when I see a really cool result in a paper, say a SIGGRAPH paper, I say, wow, I want to do that. I want to reproduce it. And I've done it. I've tried to write the code, or had one of my coworkers write the code. And we find almost inevitably that we cannot reproduce the results, because there's usually little parameters and little tweaks and little things that are missing. And oh, by the way, you talk to the author and they say, oh yeah, we did that because of this, right? But that's not in the paper. So really, it's almost impossible to reproduce results, which is really unfortunate. So again, saying the obvious, peer reviewers are expected to replicate the experiments, but as data and methods become more complex, it's very, very hard to do. And there's really only one solution to it, and you know where I'm going with this, which is open, and we'll get to that. But the question is, why did we get here? Well, a lot of it's career pressures. We're turning the crank and publishing, and we got to get stuff out there very quickly. And if we were to replicate everything, it would just take way too long. So there's a lot of pressures, financial and real world pressures, that sort of encourage us to take this behavior. But when you really start looking into it and you see how serious it is, it's very concerning. For example, in a March 2012 Nature article, two gentlemen named there who are very respected in their fields and pharmaceutical studies and so on, they did an exhaustive survey of some papers. And these papers are considered landmark or breakthrough papers in preclinical cancer research. What they found, that 90% of the papers they looked at were not reproducible. Now, okay, 90% of papers in preclinical cancer research were not reproducible. Well, what that means is, the translation of that is, pharmaceutical companies who are spending billions of dollars are looking at results in these papers and starting off massive research or drug programs and so on, and spending a lot of money, and then coming to realize that the results that are in the papers are not reproducible. They may be wrong, who knows what, but there's a lot of churn and waste going on, and it's not helping, in this case, cancer research. And I think this is happening in many, many different areas. A little closer to home, another reproducibility issue that I've seen. There's a technique in medical imaging called diffusion tensor imaging. And basically the idea is to try and create neural tracks or connectivity between parts of the brain by doing some fancy scanning. And the idea is, if you know where the fiber tracks are in the brain and you're doing neurosurgery, you avoid the fiber tracks so you don't lose function in the body, right? If you need to operate to remove a tumor or do something, you want to avoid these fiber tracks. And this is what this diffusion tensor imaging does, is it basically gives you information so you can extract fiber tracks. So what happened is, in this reproducibility challenge, we set up 8 international teams. This is not done by Kitware. It was done by some folks through the MICCAI conference. And they were given the same data, same MRI data set, and they were asked to visualize these fiber tracks. Well, the results are very interesting. I know they're a little small there, but you can see the 8 separate teams came up with 8 separate results. Some of them are vaguely similar, but some of them are dramatically different. So, okay, this is science. They're all trying to do the same thing. They're all using the same data. They're all using different methods. And you can see the diversity in results. What's right? What's wrong? What's reproducible? I don't know. I don't even know where to start. Clearly, there's a problem here. Without being able to compare methods, the software, in other words, we cannot really make sense of what's going on. And I've seen this happen again and again in other applications of scientific publishing. And then if you look at the publishing from the point of view of the internet age, you know, publishing on the web is simple. Once you get everything ready, write your paper. It's a small marginal cost to push a button and get it out there. And of course, it also supports data and software publication. In other words, the methods behind the algorithm. You know, but still, to this day, we're still doing stuff like publishing in journals, which takes 2 years. These journals typically do not have data and software as part of the publication. That's changing now, but still today, that's often true. And the costs are high. Not only does it cost a lot to publish a paper, but it costs a lot to read a paper. And not only that, there's opportunity cost, because 2 years go by from the time of sort of starting the publication process to the time that it actually appears. So there's a lot of costs that just don't make sense anymore. As a matter of fact, the costs are so high that folks like Harvard University are canceling 2 expensive journals due to expense, and they're asking professors to publish in open access journals. In the UK, the Minister of Science, David Willetts, asked that all publicly funded research should be published in open access. The World Bank announced that all existing and new publications, reports, and documents will be open access by July 2012, and so forth and so on. Of course, more recently, there was a boycott of Elsevier. I'm sure you heard about that. People are very upset with some of these big publishers because of the way they treat reviewers, the way they sort of take over copyright, the way they limit publication, and the way they don't support the true reproducibility needs of modern science. And this is really bad because it threatens access to scientific results. This is an ongoing theme of what I'm saying here. So what's happened is we've ended up with a captured science. We have publishers basically taking over the theory component, the papers and documentation around science. We have people in the methods and experimental side basically writing proprietary software, closed software. They've taken that over. And of course, there's data hoarders. I'm not sure what I mean by that exactly, except I know a lot of scientists will not release their data because they're afraid to be scooped. I understand that while you're working in the middle of something, you want to sort of have first crack at results, but I think it goes too far oftentimes, and data is held back, and careers are made out of really good data sets, which exclude everyone else. And, you know, is the data right? Is the data wrong? I mean, recently we had this, in the financial world, there was a famous paper from 2 Harvard folks, economists who basically made a claim about our financial systems and how when you approach 90% of the debt threshold, things start going very bad with growth in a country. Well, it turned out once people got their hands on the data that it was wrong. I'm sure a lot of you saw this. So, you know, when you get your hands on data, things start happening. You can't hoard it. It's not a good thing. And of course, the whole patent and copyright IP world is just a complete mess. Supposedly, there's things you can't patent, like laws of nature, physical phenomena, abstract ideas. But we all know that that line is eroding, and more of things are being patented or somehow protected. And this is eroding the public commons of science, and it's making it much harder to do science. So, the status quo as we know it right now is basically, first of all, there's too much attention on documents. We still think of publishing as being a 8-page document that we put out there, but we forget about the data and the software and methods that go along with that. We've got to change that. Reproducibility means that all the stuff goes out together, and if it's not part of a complete submission package, it's really not a reproducible document. It's not science. The other thing that's concerning is, we're in a time of emerging complexity and technology, and I'll talk about this more in a bit, but what if I want to survey hundreds of papers or hundreds of data sets or hundreds of software systems, or I want to combine software systems? I want to do meta-analysis across large numbers of results. Well, there's issues like licensing and so on, lack of open standards that prevent this from being done easily. And if we're going to sort of take the next step up in our march towards the scientific innovation, we have to be able to sort of combine previous results very easily to take that step. As I said, science is controlled and captured by commercial interests, and it's generally not reproducible. So when you see statements like this by Jeffrey Bolton, who made it in Nature, that science's capacity for self-correction comes from its openness to scrutiny and challenge, totally agree with the statement. The problem is it open? I don't know. I don't know that science is truly open anymore, and this is a real problem. So if it's not open, I'm not sure we can self-correct. All right, so I'm going to segue a little bit now and talk a little bit about the future of publishing. And the way I'm going to do this is just sort of show you some snapshot applications that I find interesting, that I think are pointing towards the future of publishing. So let's start with GitHub. I'm sure you all know about it. I pulled this off Wikipedia a day or two ago. Basically, GitHub announced that it had 3 million users and it was hosting more than 5 million repositories. So why do I bring this up? Well, this is a publication of software. Now, is this all scientific software in GitHub? Of course not. But the point is, software is being published more and more and more. Open source software is gaining a lot of traction. People are really into it. I think this is somewhat of a solved problem. Obviously more to do, but a lot of progress is made in this front. Now let's talk about data. We work at Kitware, we work with a lot of people that have very interesting data. One of our, excuse me. Excuse me. One of our collaborators at Harvard, Beth Israel Deakin Medical Center with Harvard Medical School, is a dermopathologist. And we've had a heck of an education here from her, because we're learning about digital pathology, or about pathology and the way they do it. First of all, what is done now is when you take a skin sample or something like that, they mount it on a slide and they stain it, and then they put the slide under a microscope. They do diagnosis, or they do training, or so on and so forth. But it's still to this day driven by physical specimens on slides. And this is how they train their students, their pathology students. They actually have devices like this, which are 10-headed microscopes. So 10 people can gather around a single specimen and look at the slide at the same time. This is their idea of collaboration. Okay, that is an expensive device, and it probably does a lot of things to the slide and to the whole process. That's not good. So we're working with them to sort of develop what we call data-centric computing, where you sort of gather data through some sort of a data system, and then around it you build things like visualization tools, journals, and various plugins for say doing analysis and diagnosis, if you will. And this has produced incredible results. So right now what we're doing is, there's an example of a whole slide image, which, by the way, is on the order of 20,000 pixels by, say, 5 or more thousand. It depends on the scanner, depends on the specimen. But now what we can do is scan these things into a computer system. We've developed software so we can view these huge images, and they're also image stacks in some cases, so you have 3D volumes. And then we can annotate it, so we can mark it up. In the current process of pathology, the way annotation is done on a slide is by magic marker. So people write on the slide. So now we can annotate directly in the digital image through a layering system and do some really cool stuff. And of course, we can now deliver the content through mobile devices like tablets. And collaboration is being done right now at Harvard, where basically residents gather in front of projectors and across multiple sites, and they're all viewing the same data at the same time and able to move through it, annotate it, and learn from each other. So again, this is sort of an example of data-centric computing, and this is the sort of thing that modern publishing can provide. Another example of something similar, this is the ultra-scale visualization of climate data. We work with some folks around the country doing this. And you can see at the top of the application, it all starts with data. There's a data archive. And we're developing viewers so you can actually look at the data, analyze it, process it, and do other things through various workflows. And then, once you can do that, then you can start doing all sorts of fancy stuff like displaying comparison data sets to sort of see what they're predicting on large screen devices and so on, collaborate. Another example of a recent publication was the US government released, I think you can read it up there, released through Medicare what hospital charge for certain procedures. In this case, there's 2 procedures listed, pneumonia and heart failure. And what we're showing on the chart is basically on the vertical axis, mortality, on the horizontal axis, reimbursement. And you can see there's almost no correlation between mortality and reimbursement. There's a slight, which is really scary because sometimes the differences in costs are order of 3 or 4. So you pay more, you don't necessarily get a whole lot more. Now again, is this real? Is it some bias in the data? Who knows? But by releasing the data like this, you can start analyzing and understanding what the effects are. Here's another recent tool that we developed for some of our chemistry collaborators. Basically, it's a web-based tool. It sits on top of some data. It's architected client-server. It allows people to basically look at a bunch of different compounds, visualize what the structures look like, understand what the chemical properties might be, and so on and so forth. I'll let it play through and you can sort of see where it goes. But what we're discovering at Kitware is that there's a huge potential for basically publishing. We are becoming a publishing company in some sense of the word because we're developing tools that allow people to look at data. And I think if the publishers wanted to survive, if the Elseviers and others really want to survive, they're going to have to become modern publishers, which means dealing with software and dealing with data and developing tools like this. Here's another little video, done by our friend Pat here. Pat, where are you? Nice job. Basically, again, you've got some data sitting on a server somewhere. You're in a web browser. You're able to look at it, process it, deliver it on web browser, or in a second you'll see we can deliver it on mobile devices too. There is some voice track on this, but shut down for now. If you want to hear it, you can go to our website. And here's another delivery vehicle using our Kiwi viewer technology to deliver the same content on an iPad. Sort of fun. I think you get the idea. And of course, publishing data goes beyond just looking at stuff. You want to actually be able to operate on it. You want to develop workflows that are based on data that's sitting on a server somewhere. You really don't want to move your data around because it's just too big. You really want to leave it on the server and then have your client sort of talk to the server appropriately to pass down the right data to the client. So here's a little application that does segmentation and visualization results using our Midas data integration system. And you can see it's running on the server, and it basically dumps out some new data sets, which are linked on the bottom. We then look at the data sets. They're 3D objects in this case. We can interact with them. In this case, we're looking at a segmented tumor. The next shot shows what it looks like in the original 2D scan. I want to show the volume rendering, and then I'll call it quits here. And you can do fancy stuff like volume rendering, all client server, and it's a really great way to sort of peruse data that really, in the end, is a published form of data. Now, I have said some things about publishers which probably are not completely fair, but I would like to point out that they are trying. They are trying. For example, we've worked with the Optical Society of America. They have this thing called the Interactive Science Publishing tool. You can get to it, search for it, get to it. And basically, it's special PDFs that have embedded links. So when you download a PDF paper and you click on a link, it basically pulls down a viewer and it pulls down data. And the viewer is a little thing that runs on your desktop, and then you can sort of view and get the exact same figures that are in the paper, and you can do measurement and so on. So you can reproduce what the paper is showing you in a very simple way. Elsevier, and this is our European operation in France, has been working with them. Basically, they have something called Science Direct. You can go to the web page, and if you do, I'm not showing it here in a video, but that right-hand view is actually live. It's a 3D view. So you now have a paper, and you have some data along with it, and you can view images associated with that paper. So that's sort of cool. So they are trying. They're moving ahead. One thing they aren't doing, though, is they're not really dealing with software in a very good way. So we have something at Kitware we call the Insight Journal, which is a very nice system. Talk to Matt if you have questions. But basically the way it works is you submit, a submission consists of a PDF document, source code, input data, potentially results data. This is put into a Git repository, and then what happens is automated processes pull out this package, compile the code using CMake, run the tests, generate output results, compare the results to the results data submitted, and validate whether the submission is good or not, and give it 1 to 5 stars, depending on how far it gets through the software process. Now, then it's turned over to human reviewers to look at it and actually read the paper and say, this is novel, this is not novel, and so on and so forth. So we consider this to be a really good journal because it addresses software methods, data, and publication all at the same time. So anyway, that's sort of a smattering of some of the things we're doing in the publishing arena that I think go beyond what's out there now. And what I want to sort of wind down with is, what is the evolution and where are we going to go with this and how can we all help? Well, the first thing to do is to make sure that we're ensuring reproducibility. And so we're proponents for open science, which of course includes open access, open source, and open data. And these are just foundational principles that have to be followed if you're going to do reproducible science. There's actually another sort of missing piece here, which is open access, open standards. You want to be able to get at this stuff in sort of a standard way. And those are emerging things. That comes along by default, implicitly, by using open source approaches, but it's really nice that we all build to the same standard so we can get at the data easily. The other thing that we've got to keep in mind is that there's a process of computational emergence going on right now. You've got to envision that in the future we're going to have large numbers of software systems combined with multitudes of data repositories described in untold volumes of documentation running on scalable computing systems consisting of possibly hundreds of thousands of processors. So what I'm saying is there's this scaling thing occurring that we're in the middle of. So how do we help it along? You know, if you look at things in the scientific world like multi-scale design, where you go from micro and nanoscale all the way up to product through a set of levels. For example, these materials like composite materials. When you look at the complexity of that, or you look at multidisciplinary analysis, simulation and optimization, you realize that we've got to be able to combine data, software, and knowledge about all those things in a very simple way if we're going to make any progress. So what we can do to help with all this is to make sure that things are reusable and they're shareable. And that includes doing things like making sure our software architectures lend themselves to being shared and reused, making sure we use good integration tools like Python, making sure what we do is cross-platform. We can't focus on one platform anymore. We have to make sure things are flexible. We sort of have a phrase at Kitware that goes along the lines of mobile to supercomputer. We try and make sure everything runs across all those things. We also use tools like CMake, which is a write once, compile anywhere tools, with the idea that we don't care what platform we're running, we'll make it work. Want to build really good collaboration tools, and of course, focusing on open. And open source principles, again and again and again, we have to return to them. There's a great book by this guy, Larry Rosen, called Open Source Licensing that I recommend. And he basically has these 5 principles, which I think are really great guidelines for doing any sort of open science. And I'm going to read them over. Basically, using open source software for any purpose, including making and distributing copies, creating derivative works, access and using the source code, and combine open source and other software. So these are very simple principles. And along with that are data sharing principles along the lines of a piece of data is open if anyone is free to use, reuse, and redistribute it, subject only at most to the requirement of attribute and share alike. Now, some people are afraid of sharing, especially in the scientific communities, but I just want to make one little point, which is there's a correlation between the number of citations, which is how scientific careers are measured, with sharing. And there's an article written by Steve Lawrence in Nature that points this out. And I would also say, besides trying to make things open and shareable and reusable, stop doing things like creating licenses that say stuff like, for research and non-commercial purposes only. Stop it. That's not an open source license. It's not reusable. I can't use it, Kitware can't use it, Continuum can't use it, commercial companies can't use it. It's an impediment to getting stuff done. And I know we like to think that there's a sort of a cowboy hacker in an academic environment doing all this open source development. And certainly that happens. A lot of work comes from people like that. But a lot of the open source work going on right now is funded by national labs, by commercial entities, by research institutions, and so on and so forth. So if you put in clauses that discriminate against commercial entities, you're basically doing the open source and the scientific reproducibility world a disservice, in my opinion. I would also humbly submit that drop reciprocal and viral licenses. Look, they've done a great thing. They've done great stuff. But bottom line is the open source wars have been won. They're over. Open source is the way of the future. There's no question about it. And now what we're left with these viral licenses, I can't tell you how much time I've wasted in my life basically arguing whether I can use a GPL or an LGPL in this situation or not. That's an impediment to scaling large-scale systems. If I have to think every time about what I can and can't do, and it takes a lot of my time, it's a bottleneck to scaling and emerging into a new computational sort of paradigm. So I would submit that we need to sort of use permissive licenses whenever we can, make sure that they're no-brainers to use. And of course, along that same line is make sure we create systems without a lot of dependencies, and make sure we can pull out pieces and we can do things in a reusable way. Also, make sure your software is testable. Make sure it can be tested and it's tested regularly. If it's not tested and you're not producing results on some sort of a dashboard or some sort of a way of sort of reviewing on a regular basis the quality of your software, chances are it's not reproducible, chances are it's broken. So make sure you're testing your software on a regular basis. And finally, I would submit to you that we need to stop worrying about making money. The reality is that 70% of the software market is services. Open source software, open methods are all about services. We develop really cool stuff, very complicated stuff. Very few people can use it. Anybody in this room can probably get a job in an untold number of organizations because of your skills. That represents a service market. We're all craftspeople. So, trying to protect things, put IP around things. First of all, you're only addressing 30% of the market. I don't want to be in that place. I want to be in the 70% place. So I would say stop worrying about making money, let go of the IP issues, and try and focus on services and growing the pie rather than carving out pieces of pie. Of course, the challenges are many to this sort of new view of publishing. First of all, who hosts all this stuff, right? It's a real problem. Generating this data at the scale of high-performance computing these days, where you're talking petascale and bigger, who's going to host all this stuff? It's a real issue. So I'm not sure how that's going to work out, whether it's the Google and the Amazons of the world that host it, or whether it's sort of scattered across thousands of universities and other websites. I don't know how it's going to work out, but it's a problem. We have a tool that we call Peer Review Catalyst, which helps a little bit. You plug it into a simulation system, and basically it allows you to sort of spit out only data that you want to see, and everything else is discarded. So tools like this will help minimize data, but they're not going to solve the problem. Of course, how do you maintain reproducibility in evolving computing platforms is a real issue. I mean, we're constantly upgrading our software and our systems. I know the Python community is doing the same thing. What runs now and what ran then are very different things. And as the platforms change, operating systems, compilers, and so on, things are really not reproducible like they were. I'm not sure how to address that, but it's something we have to think about if our goal really is reproducibility. And finally, how do we manage the complexity of computing systems? Because we're talking about combining hundreds of systems to build modern applications. Very difficult problem. But along with that, there's all sorts of opportunities and business models. I think there's a lot of money to be made if that's where your heart is. And I also believe that we can lead this revolution, this publishing revolution, by succeeding. I don't like to sort of tell people what to do. I like to go out there, succeed, and show people what to do. And I think people like us and communities like this can succeed in scientific computing and show how it can be done. And I think other people will follow. So, my Python story. This is my exposure to Python. When I was younger, many, many years ago, my brother was an animal lover, and we lived in the Philippines. My dad, who worked for an agency, a intelligence agency, three-letter intelligence agency with first letter with a C. We lived in the Philippines, and I didn't know it at the time because I would have blabbed and we would have been thrown in jail or something. But he managed to bribe one of the zookeepers at the Filipino Zoo in Manila, and we got a baby reticulated python. This thing was something. My brother was very, very happy. And we had this thing for a couple of years, and it grew from, 6 inches to probably towards 4 or 5 feet. And it was fun feeding it mice and all that stuff. But it came to the point one day, we kept this thing out on a screen porch in our house in the Philippines. And one day we came downstairs, my brother and I, and the python had pushed its way out of the cage. It was in a big aquarium. It was weighted down with bricks and everything, and this thing just pushed its way out. It was gone. And we were very, very upset, but that's life. You go on. Well, about 3 months later, we came down, and we also had parakeets on the screen porch. And we came down one morning, and much to our amazement, found a couple bars pushed about this far apart to the parakeet cage. And there were only 2 of the parakeets left from the original 4. And so we knew what happened. We knew the python had come back and taken a couple of the parakeets. And so I kept thinking about this story as I was coming up with this presentation, because it sort of represents something to me. And what it represents is you know, a lot of us are caged by the publishing world. You know, we're sort of put into a box, an aquarium, and we're thinking about things a certain way, you know, and it's time to get out. And it's time, you know, and then there's the scientific gems that are sitting in that cage, and it's time to get in there and pull them out and free them. I'm not sure freeing in that way, but you know what I mean. So, you know, I'm just going to end by saying we're the new scientific publishers. I think all of us here are part of the revolution. We're maintainers and builders of scientific community and scientific knowledge. And I hope you take this seriously, because if the science, the process of science, the scientific method depends heavily on us doing the right thing here. So I'm going to stop there. And oh yeah, one last thing.
Thank you very much. Will, unfortunately, we're running a little bit behind schedule, so
Sorry about that.
if you have any questions, feel free to come up and ask Will as he moves to the stage, and we'll get the sessions kind of prepared. Thanks, everyone.
Thank you. Sorry about that.
Thank you.